morning all of you. Today I am going to present my PhD synopsis. The title of my thesis work is phase synthesis of nickel bismuth system using ion beam mixing.
अच्छा, वो synthesis ठीक है spelling तो और maybe I'm wrong.
Sir, for dual phases, for more than one you can write.
Yes.
So here is the outline of my talk. In the introduction, I will explain about ion beam mixing, and I will give you a brief introduction about why we have chosen nickel bismuth system. Prior to ion beam mixing, I will be telling about the effect of thermal energy in the case of nickel bismuth synthesis, and we will discuss at what temperature what kind of phases will form in case of synthesis. And in case of ion beam mixing, we have chosen three different energy results. They are high, medium, and low energy ions. And in each case, we have performed the thermal spike model calculations, which will explain the mechanism for this mixing observed experimentally. And finally, I will summarize my talk. So, before getting into the details of ion beam mixing, we should have an idea about ion matter interaction. So, let us say there is a matter and the ion beam is impinging on a matter. There are several physical processes are expected to take place. There are recoils, backscattering, sputtering, emission of X-rays, and the emission of electrons. And in case of low energy ions, whenever ion to collide with matter, we expect two types of collisions to take place. They are elastic scattering, and the other one is inelastic scattering. So, in case of low energy ions, these elastic scattering are expected to dominate, and in case of high energy ions, inelastic scattering are expected to dominate. So, in this low energy case, most of the energy transfer happens.
Why is it like that? Why is it expected that at low energy this will dominate?
Sir. So actually, in case of maybe I'll go to the next slide and explain this. Okay. So in the case of high energy, it will not get sufficient time to interaction time will be very less in case of high energy.
So elastic and elastic collision differ by interaction time.
It will
in general for interaction, if it's high energy, it will have less time. But we are telling about elastic and inelastic. So what is your statement?
Both these phenomena are always there, but depending on at high energy, these scattering are more. That is
think about it. The other one is for interaction with nuclei, it will be elastic, but for electron it will be inelastic.
Sir, actually, in the case of low energy, what happens is energy transfer since ion has sufficient energy to interact with the atomic subsystem, it will lose most of its energy to the atomic subsystem. So that's why elastic collisions are happening at that region. And okay, so in the case of low energy ions, ion has sufficient amount of time to interact with the atomic subsystem. It will go very slowly, so it will transfer sufficient energy to the atomic subsystem.
Also to the elastic.
But less in that case.
Well, let us know.
So, in the case of low energy, most of the energy transfer happens to the atomic subsystem. That is why it is called as nuclear energy loss. Whereas most of the energy transfer happens in the case of high energy ions to the electronic subsystem. So that is why it is known as electronic energy loss. And these are denoted by SN and SE. So one can estimate these SN and SE values using a software called SRIM, which is nothing but stopping and range of ions in matter. So, for example, I have shown gold ions penetration in case of bismuth nickel structure, where we have plotted Sn and Se as a function of energy. Here you can see in the case of low energy, Sn is dominating, and after critical energy, after certain critical energy, this Se starts dominating over Sn. So this ion matter interaction has several applications.
Before you go to application,
Yes.
what is the formula associated with it? It's actually the textbook.
Like Bethe block equation.
No,
Like
the expressions for Sn and there are expressions. Where
like
is that?
minus dE by dx. Like energy loss is minus, so it is dE by dx.
I understand. So where is that expression? It's from this just two-body scattering.
Binary collision.
You should have shown that expression. It is.
I think that the equation is Bethe block equation.
Can you write down the equation?
It's very big equation.
No, you write the short version without the correction. No, okay, you write down the dependence with energy.
Sorry.
You read it longer than me. At least tell the dependence, what happens with energy, or how it depends on velocity, and how it depends on charge. Okay, velocity, you forget charge. Velocity, z. Okay. ठीक है. Doing all these analysis and things, you should not forget all the basic things. That's why you should have given the expression. I didn't forget the person in the book because there was a PhD Gautam Puri, his thesis went to that person. He pointed out something. So that's why I remember the name of it. By the way, there is a nice book. Okay, but you should tell us. Should we write down or you remember what book?
I am writing down.
So ion matter interaction has certain applications. They are like I was saying, sputtering is actually one of the physical phenomena takes place during ion matter interactions, through which one can make patterns on the surface. And doping of elements using ion implantation is very well known mechanism. And using ion matter interaction, one can also characterize samples. Something like they are Rutherford backscattering spectroscopy, proton induced X-ray emission, and proton induced gamma ray emission form. And ion beam mixing is also one of the applications on which my PhD thesis is based on. And modifying physical property is a very well-known application of ion matter interaction. One can modify structural, magnetic, optical, and electrical properties.
Is this energy is like 10 to the power 5 MeV for gold ion?
Yes.
This is extrapolated. When this energy is in, when you have in lab.
These are simulations.
Or this simulation.
What is the background of the simulations, like how that SIM program works?
Sir, they consider binary collision approximations. They consider binary collision approximations, like ion will during the so let us say you have target atoms. Like actually SIM considers amorphous targets, so it doesn't consider criticality about the sample. So randomly it will see some target atoms, and let us say if you are giving gold or whatever maybe the ion.
What is SIM? What is SIM?
Stopping and range of ions in matter. Stopping and range of ions. So whenever ion is interacting with this matter, then during these collisions, the path has to be straight. And after this collision, this energy will be. If ion's energy is less, then it will go for the other collision and so on, until and unless ion gets stopped. That is what it considers. Means binary collisions are like collision.
So then how? So then it can be also elastic and inelastic.
Yes, sir.
So both have incorporated into the program.
Yes.
So you write your equations or it is already inbuilt?
No, sir. It is actually the graphical user interface. So it is interface actually. It will in the background it will calculate all everything.
In addition, there is something called styling.
Yes, sir.
You know it is there. Why it is needed?
So actually, in principle, answer. There is something called range. So where the ion gets stopped at the target, and it's not sure that every ion will go and stop at the same region. So there will be a distribution, and this distribution, like in this Gaussian distribution, this is called data.
What are you plotting?
That is
exactly what you wait.
sorry, sir. This is range, and as a function of depth.
Depth in the unit of what?
Yes, sir.
Depth in the unit of what?
Actions.
Roughly translates to the energy study.
So in principle one can synthesize phases using thermal annealing also. So it has certain disadvantages. Like we have to use very high temperatures, starting from few hundreds to few thousands of degrees centigrade, and it has to be for longer durations, starting from few hours to few days. And in order to overcome these disadvantages, one can use ion mixing to phase synthesis, for phase synthesis. So, like, what is ion mixing? It is nothing but an atomic intermixing and null ion that can occur at the interface of two different materials during ion irradiation. Like you can see, there are two different layers A and B. During ion matrix reaction, at the interface of A and B, the atoms at the interface get mixed up and form a mixed region. Depending on the energy and fluence, one can have more mixing. So it offers several advantages over thermal annealing. So such as spatial selectivity. Sir, at the interface, since the atoms at the interface will get certain energy, so they'll yes. Like actually there are during the ion path there will be huge temperature generation, something like thousands of degrees centigrade.
That temperature generation gives this.
And in case of low energy, ballistic effects are expected. Let's say in the case of low energy, most of the ions will get sufficient time to interact with the atoms at the interface, so it will try to just push the atoms in the case of low energy. So that's how it happens. And the main advantage of this ion mixing is the spatial selectivity. Let us say if you want to have a phase synthesis at a particular region, you can actually irradiate the films at certain area and have phase synthesis, and rest can be like as it is. So which cannot be done using other.
The ion beam you are using, it also get trapped in the metal or not?
Yes, sir. Yeah.
Then you have secondary phase or something different phase.
So for that we have to choose very carefully. Like if suppose my materials are nickel and bismuth, if I know that the range is less than the thickness of both the layers, then I have to use the same element, like either nickel ion or bismuth ion, or I can use inert gas elements like argon, krypton, all this. And otherwise I can play with the energy can be such that it will go much deeper into the substrate and sit there. So it is a relatively low temperature process, so one can have this ion mixing at room temperature itself. And if we don't have to use it for days and so on, like maximum at 3 to 4 hours, if your current is sufficient enough, then at max 4 hours one can get this ion mixing done. And it is also effective for mixing immiscible systems, which is not possible using conventional techniques.
What factor decide the mixing for the immiscible?
So there is something called heat of mixing that has to be negative. If it is negative, that is called miscible system. If it is positive, then that system is called immiscible systems. let us say for cobalt and gold are invisible systems, and nickel and bismuth has negative. See, they are visible systems actually. Heat of mixing is important.
So that factor whatever you are telling, that is defined for each element.
No, for two different materials, right? Like let's say heat of mixing between two materials. That has to be negative. Sir?
How you calculate it?
Like it is actually enthalpy. So heat of mixing is nothing but enthalpy of two different materials.
So okay, so you calculate the enthalpy of one and the other and the difference.
Actually, I didn't calculate, but they are literature. So
I mean, you don't know. I mean,
yes.
This is the procedure that.
Nickel bismuth has a negative heat of mixing, so they are miscible systems. For example, cobalt and gold, they are immiscible. So, in order to explain this ion mixing, one would need theoretical models. So, there are many proposed theories for this mixing. So, thermospace model is the most successful method model to explain the mixing in all the energy regimes. So what is thermospace at first? Thermospace is nothing but a limited volume within which majority of the atoms are temporarily in motion. Like you can see a lattice structure, and along this ion path, if you create a latent track, like I was saying earlier. So within this ion track, most of the atoms are temporarily in motion. That is why it is called as thermal spike. And this theory has been developed using analogy with the heat diffusion equation. So this is a heat diffusion equation where the first term will tell you about how the temperature distributes in time, and this term will tell you about how the temperature distributes within as a function of space in space. And this is actually a source of energy, like how we give the energy. And where C is specific heat, capital T is temperature, small t is time, and kappa is the thermal conductivity, and the F is source of energy.
Similar, I just missed maybe. You did not give any background why you want to mix the interface actually.
So why you want to mix?
Interface.
So that is how we can. So the main motivation was to make nickel bismuth stable.
Go back to your SN slide. I think there were some properties you want to measure some. Modifying physical properties such as structural, magnetic, optical, and electric. That's the application. Is it?
No, actually, our main motivation was to mix nickel and bismuth in order to make the stable phases of nickel and bismuth.
Stable phases. Then that you should have actually.
You want to measure it.
So, ion mixing, through ion mixing, we are actually measuring.
Yeah. How you will organize what you why you want to do what.
I thought you want to create something with different physical properties.
Of course, they are actually consequences, so they also happen. So, using the analogy with these equations, they have developed a code where they have considered a target as two different subsystems. One is electronic subsystem, other one is atomic subsystem. So here you can see that equation has been written for electronic subsystem, and the same equation has been written for atomic subsystem. And in order to connect electronic and atomic subsystem, they have added a coupling term, which is electron phonon coupling constant. So
What is the source term?
Source term like energy of the ion. So and actually for atomic subsystem till 2011 they could not add how the energy distribution to the atomic subsystem happens. So recently in 2011 they have added it. So before that it was called as inertial thermosphere model, and after that it is known as unified thermosphere model, because now it can, earlier it was only covering high energy cases. Now since this atomic subsystem energy deposition is also added, so now it is called unified thermosphere model. So few hundreds of megaelectron volt. Yes, like after 5 megaelectron volt onwards it can be called as.
threshold velocity after doing without theory. It is called.
Tell me why there is a plus sign there and other one has minus sign.
So it is a coupling constant. So if we add one term in one atomic subsystem, say one subsystem, and we have to subtract it in the other one, like. No, we have to do that, but I think.
Maybe
So coupling term is between the electron and phonon you say.
Yes, exactly.
Okay, so it's coming from the lattice vibration. So it is related to atoms.
subsystem.
But then when you are talking about electrons, why in that you have to, okay, it is also contains the electron phonon coupling.
Yes, sir.
And atoms,
I think we have to take this from quantum mechanics. We have to take the electron phonon coupling as a spin kind of thing. So the
so that can be written as a cos verse. You can do this T minus TA or something. Okay, so writing T and TA. Okay, TP is corresponding to the temperature related to electrons. Okay, when it goes very fast, it only interacts with the electrons on the outer cell, not to the whole nucleus as a whole. But in atomic system, it interacts with the electron as a whole, but simple mode. So that's why it is like T is less than TA in case of electronic system, that will be minus. Yes, yes. Okay, go ahead. Is it okay?
Okay, you can tell us later.
This also he has to tell later. Yeah.
Okay.
It's not clear.
Maybe
You will understand.
That you just tell us, we have to look at it.
Look at it and tell about it.
So what motivated us towards nickel bismuth system? So whenever you mix nickel and bismuth, you expect to get two stable phases. They are NiBi3 and NiBi. Interestingly, both of them are superconductors at 4.06 Kelvin and 4.25 Kelvin, respectively. So apart from this superconductivity, in 2005, Mudera et al. Reported that there is a coexistence of this ferromagneticism also there in the nickel bismuth bilayers, and which was also confirmed. This was also reported in case of one of the stable phases, NiBi3, in the same in 2011, and Hermansdorfer et al. Reported that in case of nanostructured NiBi3, they observed CSF. However, in the same paper, they reported that for bulk NiBi3 doesn't show CSF. Whether this NiBi3 show coexistence or not still under debate. So it needs further exploration. And apart from this interesting physics aspects, one would also find technological applications such as galvanized coatings. These are the coatings to avoid rusting.
So Shiva, you know from your basic textbooks that superconductors are not ferromagnets. Why?
So normally, in principle, only 1% of magnetic impurities can destroy complete superconductivity by destroying the Cooper pairs, which is called pair breaking effect.
We don't need impurity in a single phase material, which is pure superconductor. Now let's find out what is the magnetic property. Some basic things are there which tells you that it cannot be ferromagnet.
Right.
What is that? Why superconductor and ferromagnet don't like each other?
Actually, the exchange field from the magnetic field normally destroys these Cooper pairs.
Okay, you will tell us this also. But I like to know in the Mudera paper, the PRL paper, when they say there is coexistence. So what made it coexistence? It would be good to see some background.
So for that actually they
So
suggest
what
that.
happened that finally they could coexist?
Yes, sir. They suggest that actually G1 splitting of carrier bands happen because of Zeeman splitting of carrier bands.
Carrier bands.
Carrier bands, because of which this minority and majority Fermi surfaces they won't be similar anymore after Zeeman splitting. So
You know, famous effect. Superconductors are excellent diamagnets, right?
that's right.
What is that effect?
Meisner effect.
So now what happened? The Meisner effect does not work. Just the Zeeman splitting of the carrier bands.
Actually,
I don't believe it.
no. Actually, in case of superconductors, magnetic flux cannot penetrate, but there is certain till certain length it will penetrate. That's called penetration depth. So, if this Zeeman splitting occurs in case of Zeeman splitting of carrier bands occurs, then this magnetic flux can penetrate sufficiently large into the superconductor. That is what they say in this
And
case.
what was the ferromagnetic Curie temperature in that compound? Nickel bismuth by Mudela?
And this one, Curie temperature there is mentioned.
So superconductivity is about 4 Kelvin.
Right.
Now what about the Curie temperature?
So there is mentioned in that paper.
Any other paper you mentioned?
Like this was the only paper on nickel bismuth barrier, and all the other works are only on marble.
Nickel bismuth field. So it has a good, sorry, this superconductor tension, what is tension and pressure?
4.06.
And in case of this one, nickel bismuth by a,
Oh, they have shown it was 4.2 Kelvin.
so it could be that some interaction there also.
Actually, in principle, it is there, but they didn't report that time.
That could have,
actually-
that was the initial study, that could be.
Yes, sir. That
I
is,
don't know, I have not seen this picture.
yeah, it must be the case, sir, because actually whenever you deposit bismuth and nickel, there is a intermixing at the interface during deposition itself. I will explain that.
So none of them reported about the Curie temperature of the ferromagnet.
Maybe I have to check, sir. I think they have.
Yeah,
So how did they know it's a ferromagnet?
So-
Showing ferromagnetism.
They have done spin polarized dancing measurements.
What was the observable the plotted in X and Y axis?
So that is dV by di, conductance or voltage. So like there is
That is for the superconductivity.
that is not for the ferromagnetism.
That is for the superconductivity.
it's a superconductivity itself. I think there will be
So
dV.
how did they prove it has ferromagnetism? Must have measured something. To say that they show that superconductivity and ferromagnetism both exist. So they must have done some measurement to prove that it is superconductivity, some measurement to show it is ferromagnetism.
In principle, one can measure magnetization and function of.
In principle,
But actually, I think in the paper they have only mentioned this spin polarized dancing.
So that doesn't tell about ferromagnetism.
No, that is for the superconductivity.
Yes.
But again, nickel bismuth, it is well known that it will be a ferromagnet.
well known by
Because nickel is ferromagnet.
measuring how.
Means any magnetism. Any magnetism.
What's the temperature?
Magnetism was a temperature.
So that is the temperature.
Yeah.
Because
No, that's
very
right.
high temperature, that
Right.
means people do not measure.
In this paper, actually, they have shown like they have measured m as a function of flow.
You have made the measurement, then you show your result. What temperature is asking.
See, I'm just curious to know if it is the similar temperature, it's a very high temperature.
Yes,
Nickel has temperature like 1000 Kelvin. No, it is 11 point something.
Okay, it is 11 point.
Yeah, in case of the fast
You want
reaction.
to check out 11 point.
And
Okay,
you will
he will show his measurement.
I have not shown it here, sir.
He will
Because
show you thesis.
yes.
Tell later on.
Actually, what happens is like I'll tell you. M as a function of field actually will have hysteresis loop. But at the lower,
At what temperature?
sir, below TC, like 2.5 Kelvin.
So the question is all about thesis.
No, I'm saying about superconducting. I'm saying TC means superconducting transistor, so not Curie temperature.
So you measure the hysteresis below 4 Kelvin.
Yeah.
Okay.
So it will be like,
ठीक.
in principle, it will be like this. And actually, in the case of if it is having superconducting property also, then it will go like this and it will give a So that is actually kind of, that is the signature if it has superconductivity.
This measurement at 2 Kelvin you will have done.
Not room temperature, sir, like 2.5 Kelvin.
See, Shiva, so you get a deep, na?
Yes.
After that deep it is photoconductivity or no?
No.
Very big S actually.
Oh.
So the second one that I explained.
Yeah, even we have measured in one case. So whatever the work has been done till now was mostly on the bulk, except this paper it was only on bulk, and the ion mixing of nickel viscous system has not been carried out. So that's why you are interested to study the ion mixing of nickel viscous. And so here is a phase diagram of nickel
So there
viscous.
is only within one things. Time period of the temperature doesn't mean anything. Time period of the temperature alone is energy. It doesn't have meaning.
In all these cases they have to use longer durations. Like some cases it was like months also, and in this case actually they have made this NABFE at 1000 degrees centigrade. So we can actually reduce both these things using ion mixing. 1000 degrees centigrade. 1000. Sorry, sir. It is 1000 degrees.
For 7 minutes. To make this place.
So here is the phase diagram of nickel viscous system, and here 271 is the melting point of bismuth, and 1465 is the melting point of nickel. So from in this direction actually you have nickel 0 to 100%. Now whenever you have 25% of nickel and 75% of bismuth, given a temperature of 271 degrees centigrade, you expect to form NiBa3 phase. And when we have 50% of nickel and 50% of bismuth, and given a temperature of 471 degrees centigrade, we expect NiBa phase. And after this temperature, this NiBa3 compound will decompose into NiBa plus 2 bismuth atoms. And above this temperature, NiBa will be constant, and NiBa will exist, but NiBa3 will decompose. So
how does one experimentally know this exists? All this you said here it will exist like this.
yes, sir. Like people take the composition of nickel and bismuth separately, and then they anneal them.
Preparation of sample. What measurement you will make, which will tell you that it is NiBa3 or NiBi.
EPMA, electron probe microanalysis. Like actually it is something. It is nothing but SEM only, but they will measure the energy of X-rays. It is, and then they will say which phase actually is having.
Energy of X-ray in y-axis.
Yes, sir.
What is in x-axis? I just want to know what is the measurement.
No, they will
This
just.
is a simple head.
Exciting enough.
Even XRD also we can say. But in this case, earlier whatever they have done with EPMA.
I agree.
From XRD you can say
You did learn from your presentation. Okay. Follow. What is the measurement?
XRD will also tell that.
Will also.
Yes. EPMA is actually also they are all they have done is EPMA where let us say XRD can be. No, but all these measurements are done using EPMA only. Not
That is asking for general पूछ रहा हूँ मैं थोड़ी ये plot कैसे आया? General thing how does one know?
XRD से
Can XRD give 100% separation?
phase separation.
No. That's why you will do this second order measurement.
So in the case of thermal annealing, we have chosen nickel bismuth tinctures and we have annealed them at different temperatures from 500 to 800 degrees centigrade. Here you can see the surface morphology of the as deposited.
How did you see this? How did you see this? क्या measurement?
Sir,
SCM. What is x and y axis? The x and y.
Sir, इसमें
It is two dimensional.
This is actually surface morphology.
Surface morphology, that means x, y, and what is the sets, their intensity. क्या है?
X and Y both are in distance.
Yeah, electrons.
And then white and black,
White and black actually will give you about height difference.
intensity.
Height difference.
Acha, height. So this is like how rough is the surface.
Yeah, how rough is surface and how the surface is like.
This is height difference. This is you are measuring two different phases, na?
No, actually in this case I'm not showing like phase analysis using this.
White and black are with two different phases. It's not a height difference.
Like both the things are possible. So one is height difference and another one is.
Yeah, means height difference possible, but in this case, what you are showing it's not height difference.
Sir, actually it depends on whether we are taking the secondary electrons or backscattered electrons. Right? The secondary electrons, then we can say it is.
What is in this figure of like both technical? Just explain what is that color difference.
Actually in principle it is both. Like height difference and then composition also.
So what you are seeing here, it is like two different composition or same phase with height difference.
Sir, I am saying only about height difference here. Actually, I am not confirming with this SEM about composition.
In these images, can you probe this NIBI3 interface from here?
No.
Then why are you not telling about that you cannot assure that whether it is phase or not? It is simply morphology and due to the uneven surface, it is giving the contrast.
So after annealing, actually we see agglomeration of the films, and at the case of in the case of 800 degrees centigrade, we see a water-like surface.
after पहले heat करके ठंडा होने के बाद just one
Right.
not at that temperature, no.
So this is the excited data. As deposited samples, as deposited films show the presence of nickel, silicon, and bismuth. And after annealing, we see presence of both stable phases, NIBA and NIBA2. And these phases are stable until a temperature of 700 degrees centigrade. After that temperature, like I was showing from the phase diagram, this NIBA3 decomposes into NIBA and to bismuth.
Where this measurement was done?
In chemistry.
But you have also nickel oxide phase.
Yes, sir. Like oxide is there.
They will constitute magnesium of nickel oxide.
It will be. We have not done something like that.
It is small amount and nickel oxide is
Anti-thermal.
No, but nickel oxide also gives distances too. There are the error papers. Nanoparticles or all these things. Can be, maybe as
I asked whether this is. So, in the case of ion mixing, let me start with the high energy ions. Before getting into the details of ion mixing in case of high energy ions, during deposition itself, we have seen a spontaneous formation of NIBA layer. So, it was a very interesting thing. For the first time, we have observed it, and it was published in this chapter. And so, actually, the spontaneous formation of NIBA3 happens due to a mechanism called diffusion reaction. What happens is, whenever bismuth is depositing on nickel, the atoms of the interface bismuth will diffuse into nickel at first, and then it will react with nickel. So that is why it is called as a diffusion reaction mechanism. And there are two possibilities for that diffusion process. So either nickel will diffuse into bismuth or bismuth will diffuse into nickel. So one would expect due to less atomic radius of nickel, nickel will diffuse into bismuth. But it is other way around because bismuth is known to be a very volatile material, and its melting point is very less. So due to this large temperature difference, the second one is actually most possible one, which was actually proposed in this book. And let's say at the interface of nickel and bismuth, during deposition, there is a possibility of formation of NIBI, and we cannot exclude the possibility of NIBI. Of course, we have not seen that NIBI phase in this case, but in the latter stage, we have seen there is a less amount of NIBI formation.
What is it like? What is the thickness of the interface? This spontaneous this
can I tell that in the later stage? Because actually,
You are.
that is the main concept. So, in the case of high energy ions, we have used 100 MeV gold ions, and as a function of ion fluence, starting from 1E12 to 1E14 ions per centimeter.
Using what facility?
From IUS.
IVS. What is the terminal voltage of that accelerator?
That is 14 megavolt. 14
14
megawatt.
MV. And what charge state you use?
7 plus.
7. And it can go down to what? That's the maximum terminal voltage.
Right.
How low it can go down? You have seen that system?
Yes.
Can you tell the main component? What is the extractor voltage? That's the minimum it can go.
Extractor voltage in that case I don't know.
But what is the source of gold ion? How is the source?
For the cathode, like normally it is like it's MC6 multi-cathode source of active ion by Cesium structure.
Then?
So that's how like there will be cesium ions.
So cesium will sputter and gold will come out, so something has to extract it. So that was the voltage.
Extract voltage. Yes.
Ah.
That voltage I don't know.
Then now what is the pressure at which the accelerator is kept?
Accelerator will be like 10 power minus 7 million.
7 or 8?
So minus 7.
Huh?
Minus 7.
The accelerator went to 8. So what pump leads to that pressure?
Using turbomotor pump we can.
You have seen that setup.
Yes, it's very good.
Then it's a pelletron or what type of
It's a tandem accelerator.
Tandem accelerator. How it works?
Sir, we have two cycles of acceleration columns actually. Actually, it is a
That's the accelerator.
accelerator tube.
Okay.
So, actually, there are two.
Where is the stripper placed? Where it strips the gold ions?
Actually, there is like many coils. In between, actually, we will give us potential difference. Like
Where is the gold ion stripped of its electrons?
this was what I'm
Ah,
saying. So, in principle, in the starting we make gold negative ions, and then till this half of this portion, we accelerate the gold ions. After this, we use which is called a stripper gas. This will actually take out most of the electrons from the gold. So in this case, it was gold surplus. So it has to take 8 electrons away from the gold ions. And then you will have files here, and it will accelerate from further.
Have you seen where the SF6 is stored?
Like very big container.
Do you know why it is kept like that?
It is toxic.
Usually, suppose there is leak, because it's a safety issue. If there is a leak in SF6, so what will you do? Will you crawl down or you will stay up?
We have to crawl down this.
No. SF6 happens on the floor.
Because
Sorry.
it go down.
Yes.
Huh?
Yes. Sorry. Sorry.
Okay, go ahead.
So here you can see SE amount of SE is actually dominating over SN in this case. And the range of ions is more than 6 microns in nickel case, and in bismuth case it is more than 5 microns. It will go much deeper into it. So the surface morphology of the films can be seen here. So as deposited, the film is actually very smooth, and then after irradiation, the films of 1 equal ions per centimeter square, you can see porous-like structures on the surface. And then with increasing ion films, we have estimated the distribution of these flows as a function of ion films, and it was it keeps on increasing with increasing ion films. So these porous structures are forming due to out diffusion of bismuth. Like along the ion track, you will have a molten-like zone. Since bismuth is very volatile material, it is expected to go out from the surface. So that is how we can get this morphology.
you have written average size. How
Yes,
did
sir.
you get that?
Like with this distribution is in the
Gaussian distribution. And then how did you get the error?
that's fitting error. Fitting error, so like
Whatever the computer did.
yes, standard deviation.
Okay, go ahead.
So these are transmission error from microscopic cross-sectional images where the white color contrast is showing thin film, and below which is silicon substrate and above which is glue in all the cases. A, B, C are showing for as deposited and the lowest planes and highest planes. So we have drawn a line across this cross section and we have done EDAX measurement. In EDAX means energy dispersed to X-ray spectroscopy, where one can see the elemental composition.
It with the PM. It with the PM.
Yes, sir. So these are the elemental line profiles. So for silicon, nickel, and bismuth are shown here. So we have drawn a window of cross lines to emphasize the intermixed region of nickel and bismuth. Here you can see with increasing ion planes, the width of this window is increasing. It is almost 50 nanometer of enhancement with increasing ion planes, and which is actually 20% of total thickness of film. However, the information from TEM is very local. So in order to confirm whether it is there throughout the sample or not, we need to perform RBS measurements. So before getting into the results of RBS, I would like to give a brief idea about how RBS works. In principle, we keep our samples. So let us say our sample is here, and we use helium ions as a projectile, and then if the cross section of the target atoms is sufficiently high, then these ions get back scattered and will be collected at the detector. And the scattering angle will be around 165 to 170 degrees centigrade. So the energy of these back scattered ions can be achieved by using this equation E1 equal to K T naught, where K is a kinematic factor, which we can see here. In this case, we have chosen. Normally, you can see how this RBS works. Like ion beam will fall like this, and after getting back scattered from the target atoms, they will be collected at the detector. So in our case, we have chosen 2 NeV helium ions and these back scattered ions were collected at 165 degrees.
So why didn't you use a carbon for backscatter?
Sir, projectile mass should be as less as possible.
So how it depends?
Sir, this is the factor that decides actually. If M1 is the projectile mass, and
Why do people use helium? Why don't you use oxygen, nitrogen, or maybe nickel itself for backscatter?
has to have very less cross section compared to the target atoms. I think means scattering cross section.
You don't show any points or anything, I will understand that.
So this is the formula.
Okay, right.
So
There is backscatter, there is also forward scatter.
if yes, there,
When?
it has to be very thin. The sample has to be very thin. Then only it can pass through and like.
Okay, tell me that scattered. Okay, so you will tell me that, huh? Why
we have
make larger size, what happens? Then what type of detectors can you use?
it is actually silicon barrier detector. Silicon barrier detector.
Tell us some. Just quickly.
So actually you will have a PN junction of like N-type silicon and N-type silicon deposited on P-type substrate. So it will have a PN junction and detectors. So whenever this ion is backscattered ions are actually colliding with this PN junction, then there will be a generation of electron voltage, and this current will be these electrons will be passed through the junction, and that will be bonded. So that is how it is.
But to keep it at some temperature or at room temperature.
So a typical RBS data would look like this. So higher the atomic number, higher the energy of backscattered ions. And here you can see for case of gold, actually it is sitting at a higher energy, and silicon at medium energy, and in case of carbon, it is sitting at a lower energy side. And if your thickness is more, then the distribution will be like this. Otherwise, it will be like Gaussian shape. And one can get depth profile and information of thickness and the composition of the samples and all using this RBS. So our RBS data would look like this for crystalline and all the irradiated samples. This is actually bismuth peak, and this one is nickel peak, and this one for silicon substrate. So after fitting these RBS data, we are using rough simulations. We can get the depth profile. Atomic fraction as a function of depth.
What is channel number?
So it is directly proportional to energy.
Which channel?
Sensor.
Channel.
Actually, we use the multi-channel analyzer.
How it is related? How will you relate? There are some numbers. You say it is related to energy. How will you relate? No, tell me.
This channel number equal to K into kinematic factor into energy. The energy of the incident.
So you need to calibrate.
We need to calibrate using two different spectra. The energy of ion. So
maximum channel number is
2048. So, like Ajay sir was asking about what was the thickness of NIBF layer. So here you can see in the case of all the samples, you can see bismuth and the nickel ratio is almost 77% and 23%. It means it must be composition of both NiBF and bismuth from the surface to a depth of almost 15 nanometers. So it is mostly aligning the surface to interface of nickel bismuth. So actually you can see this is actually a bismuth depth profile, and this one is for nickel. It goes like this, and from the surface to a depth of almost 50 nanometers, you can see it is almost constant, and it must be NiBF layer. And then it is mostly 50% of nickel and 50% of bismuth. It must be either NiBA or equal amount of contribution from nickel and bismuth. And after that, it is mostly nickel, and a few bismuth atoms are there in the nickel layer. And we have zoomed this part to show enhanced region. It is almost 3 nanometers in this region and 7 nanometers in this region. So total it is 10 nanometers. And out of total thickness, it is almost 15% of enhancement in the thickness. So
why did you choose 35 in this case? You take 25, is there any reason?
so we have randomly chosen.
And this thickness also you can verify from this TM also process on TM.
Yes, yes,
So you verified that?
yes. So that image I have not shown here, but we have done that.
So this is taking the same amount of NiBA from the.
Can you control the thickness by, so you are getting the 50 nanometer.
Yes,
Can you vary that thickness by any condition?
yes sir. We can monitor the thickness during the deposition itself using a quartz crystal monitor. So
No, my question is if you want to make synthesize 25 nanometer of.
okay, yeah, this one. If I want to have more thickness, okay. So energy can be the parameter. Maybe you will see in the next slides about what energy will play the role. So it is almost 50% of enhancement in the about total thickness. And we have performed realistic thermostat model calculations in this bismuth, lithium and nickel thin separately, and then together keeping bismuth and nickel together. So here you can see lattice temperature as a function of time. So we have drawn a horizontal line to say about melting point of bismuth, And in case of bismuth, it is reaching melting temperature in most of the ion track radii, for most of the ion track radii. And in case of nickel, this melting point is around here, and which is the lattice temperature generation is very much less than the melting point of nickel. So, if you see both of them together, we have plotted maximum temperature generated during ion matter reduction over melting point of each layer as a function of distance from the surface. So here you can see at the interface of nickel, bismuth and nickel, bismuth is reaching, so if this ratio is more than 1, that means the material is in molten phase. If it is less than 1, that means the material is not in the molten phase. Here you can see it is more than 1 in case of bismuth, so that means bismuth is reaching molten phase, whereas nickel does not. So the summary of the first part is like since bismuth reaches molten phase while nickel does not, and nickel does not reach molten phase because it is well known that nickel is insensitive to that ion beam at that particular energy region, and so therefore one would not expect mixing to happen at this energy region. However, we have seen enhancement in the mixing. So we attribute that mixing to the ballistic effects and interface mediated mixing. Ballistic effects means even though SN contribution is sufficiently less, but it still has some number, so it will also contribute some mixing. And then at the interface we have LiVA3 that we could not give into the calculations because of lack of parameters, axonal parameters. So that is why maybe that could be the reason for enhancement and mixing. So since we have seen nickel as insensitive to the higher energy case, in the case of medium energy ions, we would like to confirm whether nickel is sensitive to the ion beam at this energy regime or not. So for that purpose we have chosen nickel layer and then 2.2 MeV gold ions as a function of ion clearance. And here you can see Se and Sn are almost in the same order of magnitude. So these are the atomic force microscopy images. So as the positive samples show nanostructures distribution on the surface. After irradiating these films with gold ions, we see drastic changes with increasing ion clearance. At the highest clearance, we see a mortar-like surface on the surface morphology. So, sir, so one can extract power spectral density after performing a Fourier transform on these surfaces. So the power spectral density will give you the information about what was the growth mechanism for this such evolution, and then lateral size of these grains. So here you can see PhD as a function of spatial frequency. Spatial frequency is nothing but how often you are getting when you are traveling from one direction to other direction, how often you are getting the grains. That will be a measure of that will be the measurement of spatial frequency. So here you can see there are two regions. One is actually plateau region, and then it will sharply fall. And this sharply fall region will give you the mechanism for what was the reason for growth. So actually this will vary with PhD vary as a function of frequency according to this equation. A into Q power minus gamma, where A is a constant and gives spatial frequency and the gamma is power law exponent. This power law exponent will give you the actual mechanism responsible. So if gamma equal to 1, mass flow was responsible for such evolution, and if gamma equal to 2, evaporation condensation, gamma equal to 3, volume diffusion, gamma equal to 4, surface diffusion. These are the since we have seen mostly 3 and 4 dependence of power law exponent in these cases, so I have tabulated them here. In the case of system,
So that how did you do this plot? How
yes,
is
so
it done?
this one.
How was the PhD calculated?
So after performing Fourier transform on these surfaces, Fourier transform on It is actually a high difference. Normally AFM is nothing but a high difference.
So what was the data in X column, Y column, and then what did you do?
Okay.
You must be having three column data. Yes.
Right.
X, Y, and height.
Right. Y is high.
Then what did you do?
Sir,
Then what did you do to get PhD versus Q?
okay. Uh,
Analysis software से हो गया था या?
Software से हो गया था सर बस.
No, we done. You should know that how it Fourier transform. You
None.
certainly know,
Right.
but how it is done to get to this y-axis and x-axis.
Yes, sir. So the software considers as a function once you are going from one direction to other direction, how often you are seeing the rays. That is spatial frequency. And PhD is the slope of line joining between two such grains. That will, so it will take the slope of two grains. Let us say you have
Anyway, you have a look at it. Simple way how it is done. You can tell us. Good for know how it is done.
normally actually let us say your surface is like this, and so of this kind.
Directly, can you say something from your reactant results? There is some variation.
So high difference maybe you cannot see from class system. So I am saying it this is line joining between two such grains, and the slope will be considered for PhD. That is positive density, and how often you are getting such grains, that is actually spatial frequency. So in our case we have seen in the case of crystal sample, because gamma value was 4. So surface diffusion during the deposition was responsible for such nanostructure. So for such nanostructure. So for such evolution, and then after irradiation in the blood lenses you can see.
Take whatever you want heaviest.
Okay, so in the blood lenses volume diffusion was the responsible. So in the case of lower appearances, volume diffusion was responsible for such evolution. In case of higher appearances, surface diffusion was responsible for such mass flow. And then you can see the RMS roughness values. Initially it is decreasing.
Which value? What the value to declare? Which RMS?
RMS roughness, root mean square roughness of
So that how is that measured? That AFM gives.
AFM.
How is it measured? Software दे देता है. RMS of what?
Actually, I think we have to consider about high difference. It is actually the fluctuation is the high difference. Fluctuation is the high difference.
What did you plot whose RMS is this? RMS is root mean square. Right? So what did you plot? जिसका RMS ये लिए बता रहे हो 2.5 का RMS. कौन सा डिस्ट्रीब्यूशन का RMS और इसका कैलकुलेट किया RMS?
High distribution.
Have you converted your
Surface morphology into some special high distribution variation. From there, did you do some calculation? From the FM images.
Here we are talking.
No, normally.
Normally we have to see.
If you use AFM, you should know what you're
Once
doing.
we
That's
have,
right.
once we have AFM image, then we just convert that AFM data into the numbers, right? How does the height variation varies? After that, we do some.
So you will tell us this, because when we certify that we have done AFM, we should know how RMS is.
So we have done RBS measurements on all these samples, and we have extracted depth profiles as a function of all the antigens. Here you can see it is actually black color one is for crystal. It is only there from almost from surface to almost 7 nanometers, and then it is not there. After ion freons, actually nickel is penetrating much deeper into the substrate. That means nickel is not insensitive at this energy level. So even thermostat model also suggests that it is actually reduces more than phase. Maybe I'll show you the results.
Before that, you see, the sample as such had the higher RMS, only after 2 into 10 to 15 it crossed. Why? It became more smooth, or maybe. So increase in RMS means more rough, or
Increasing RMS surface means more rough.
so it became more rough.
Yes, sir. Initially, actually, it was due to volume diffusion. Like the grains in the surface, actually, they are trying to diffuse on the surface.
So surface diffusion increases the roughness. Is that what you are saying?
Yes, sir. Like the grains are actually diffusing very rapidly on the surface. That's how.
And volume diffusion decreases. Is that what you are trying to tell? I mean, you see roughness has decreased, and you show that the exponent is 3 and volume diffusion.
Right.
Is that what we can say that?
Yes, sir. It must be the reason. Yes.
Then by measuring roughness, we can also say what type of diffusion. You see, roughness decreased.
Yeah.
Oh,
So
I don't know. I'm just asking about.
yes, sir. So the result.
How many more slides you have?
No, no.
Yes,
our
sir, 10 more
experiment,
slides.
it will go as long as
it goes.
Please don't
Nine
ask.
more.
No, no. We will go as long as possible. The last time we will look at the student.
9 more slides.
I know 10 or 2.
Okay. So the results suggest that actually nickel is not insensitive. So we can further proceed and mixing of study of annual mixing nickel substitution. In this case, we have chosen 7 nanometer of nickel and 7 nanometer of small, where we have chosen 1 mV nickel ion as a function of ion phase. So here in this case, you can see.
I have one question. So you have shown earlier that when you deposit nickel and bismuth, automatically there is a nickel diffusion. So then you are doing the ion mixing. So that increases the interdiffusion thickness basically.
Actually, the spontaneous layer formation is not complete in principle. So it is actually stopped after certain time. So using ion mixing, we wanted to completely mix both the layers. So that is what.
So let's say in the 7 nanometer case,
Yes, sir.
with the, before you do the ion implantation, what is the expected thickness? I mean, diffusion.
Actually, it is very less in this case. I'll show you the depth profile in the next slide. So it is very less in the case of since the thickness is very less.
So how it is?
So no, it is actually 7 nanometers in this case. Earlier it was 35 nanometers.
In this case, what is the interdiffusion before ion implantation?
Yes, sir. Maybe I'll show you in the depth profile.
Just show me first that one, then explain.
So here it is.
The pristine sample.
Yeah, this is actually the bismuth layer profile. So this is nickel. Actually, it is almost 0.98 atomic fractions. It is even in this layer also we see formation like nickel diffusion into bismuth and sometimes
If you expand your central line, you will know that it will value 1 to 2 nanometer. Exact around within a nanometer.
But even in this layer also there is a nickel layer, but it is very less. Nickel actually also there in this layer also.
Okay, so 1 to 2 nanometer is already interdifused.
Yeah, actually it is not complete layer, sir. In principle, what happens is it will try to diffuse as much as possible. So since they are since they have negative beta mixing, so depending on how much energy they have, they diffuse that way. So it cannot be said.
I understood that. So I'm actually trying to understand more.
Yes, sir.
So 1 to 2 nanometer is the interdiffusion in the crystalline sample. Now with the ionization,
Yes, sir.
that thickness also increases.
Yes, sir.
And the phase becomes kind of single phase or so.
Actually, it is not single phase, so that has to be.
That's why actually it always means you should verify with the TF, the process on TF. So that means this three phase, not NISER or NIST, all these things. I mean, you can clearly see all the thickness on this thing.
That's
Okay, you can go back to the previous slide.
It's coming.
yes, sir.
Distribute.
So
So you have done some, that's why I'm asking.
yes, sir. In the first case we have done to confirm whether it is actually there completely or not.
System EM will very hard to do in 150.
So for the first case we have done. After that we could not.
That you did in IL.
No, sir. In SIN.
Yes, sir.
So in this case actually we have performed the SRD measurements on all the samples. Here you can see in the Christian sample also we have the stable phases NAB and NAB. But after increasing ion beams, it must be ion beam is actually amorphizing the field, because whenever this ion metal interaction happens, there is a huge temperature generation, and that will quench very rapidly. Within 10 power, the quenching rate is 10 power 12 Kelvin per second. So that is very huge. That can actually create amorphous phases.
So it's very nice that here you don't have this nickel oxide phase.
No, sir.
So previously you have. So these are better samples.
So this is very hard to use our customer, but you will not see the exact sequence.
So the depth profile is so that it is this much depth profile is almost it is almost 1 in case of surface, and it is almost 0 in the nickel layer. But after increasing ion fluence to a fluence of 5 into 10 power 15, you can see it is naturally coming down. It is almost 0.63 to the ratio of bismuth and nickel is 0.63 and 0.37. So that means actually it is responding very rapidly to the ion beam. That means this is the enhancement region after ion degradation. So 6 nanometers is the enhancement in the mixing, and which is 60% of total thickness. So we have performed unified thermosphere model calculations in these cases. Here you can see we have plotted the maximum energy per atom as a function of distance from the surface. So in order to drive bismuth and nickel to molten phase, we have to supply 0.26 electron volt for nickel, and for nickel it is 0.62 electron volt. So if you supply that much of energy, we can drive these layers to the molten phase. So that I have highlighted, this pink color highlighted region is more than these values for bismuth and nickel. So here you can see almost 4.5 nanometers of molten phase in case of bismuth, and then 1.2 nanometer of nickel, 1.2 nanometer of molten phase in case of nickel has been seen. So this must be the reason for enhancement in the
So
mixing.
now the 6 nanometer here is NIBI 3 or also NIBI.
Sir, in this case actually it is in 550 nines per centimeter square. It is NIBA most probably, and after that it is till here only it is NIBA. After that it is random.
So about 3 nanometer is NIBI.
Yes, sir.
Then you cannot say that this is an annual mix of parts.
In this case, as you have seen earlier, SE and SN are comparable. So the synergistic effects of both SE and SN is expected to give rise to such large molten track radius. So in the low G case, we have chosen 200 kV argon ions. As a function of ion fluence, 540 to 170 ions per centimeter square. Here in this case, you can see SN is dominating over SE. And the range of these ions.
The same accelerator.
No, sir, it is in IUSE, low energy implanter.
Low energy. How did they produce argon?
Actually, they use
Snakes.
no, not snakes. That is easier ion source. Electron cyclone. Electron cyclone.
What happens? That's the name.
Okay.
Okay,
Okay. Yeah. Yes, sir. So, in this case, we have performed the SEM measurements. So you can see at the lower frequencies, after the irradiation, we have seen a small layer surface morphology. It was due to sputtering of surface atoms, and these films are actually hydrophobic in nature. That means one can actually use them for anti-rust, to avoid rusting. This coating can be used in preventing rusting. And after this phase, it is mostly smoothen the surface because of large sputtering. Most of the bismuth layer is sputtered. That I will show you in RPS measurements. So XRT measurement suggests that in all the cases we have nickel bismuth along with NiBa3 formation.
So in this case, there is no structural diffusion for
That is there, but it is very much, like too much, so that it will remove almost all the bismuth layer, top layer.
the gold ions energy was higher than
No, actually in this case what happens, it is low energy, so ions will have sufficient time to interact with the surface atoms, so it will reject the surface atoms, which is nothing but sputtering.
Surface is hydrophobic or hydrophilic?
So it is. So we have to measure the contact angle measurements. So the angle is more than 90 degrees. Yes. So here you can see this is RPS data where you can see this one nickel and silicon peaks. So at the highest frequency case, it is mostly bismuth layer is almost not there. That means it is sputtered out all the layer. Only and then the nickel actually is trying to move towards the higher energy side. That means there's a mixing in this case.
These open symbols are simulations.
Some open no. Everything is actually experimental details, experimental results.
Different
fluids. So we have fitted this data using ROM simulations again. So here in this case we have seen the enhancement in the mixing is like 12 nanometers in this case at this design, and 6 nanometers in this region, and 2 nanometers. Overall it is 20 nanometers. So 20 nanometers is almost 25% of total thickness. So to understand what was the reason for this mixing, we have performed thermostat model calculations where we have seen like 3 nanometers of latent track in case of bismuth and 1 nanometer of latent track in case of nickel. So here in this case it is less, ion track radii is less. That is the reason why we have seen less mixing in this case compared to the medium energy.
What is the maximum temperature?
Maximum in this case for bismuth.
Same for the same fire. 200 kg and 100 kg.
Says,
These temperature rise.
no, not the same. They are not the same.
It's same for 200 kg and 100 kg.
No, they are not the same. Okay, so we have given the amount of energy per atom here. That is in case of nickel, it reaches 1750 Kelvin, which is more than little higher than the melting point of nickel. In case of bismuth, it reaches around 700 degrees. So in this case, the implement in the mixing due to combination of both ballistic effects and thermostatic effects.
Actually, initially you showed that unified thermostatic model. So you have two equations for electrons and atoms. Now, when you always say that we have made the model calculations for this case, what do you exactly do?
Sir, actually,
Because there are a lot of terms, the electron proton coupling, all those terms.
so actually in the case of high energy,
Let's go back to that slide.
yes. in the case of unified thermostat model, you have a contribution of both electronic energy loss and then nuclear energy loss. Okay. So how much energy has been deposited? This AFRT is energy deposited into the electronic subsystem, and this one for atomic subsystem.
Yes, but how, let's say you take its example.
Yes, sir. So in the case of high energy ion, SN is SE is too much, means which is dominating. In that case, one can neglect the atomic subsystem energy given to the atomic subsystem. That is very less. So in that case, this BF40 term was not there. That is that was called as inelastic thermostat. If you include this nuclear energy loss term also, then you have the energy term. That is what is called inelastic thermostat. So in the case of high energy ions, we have chosen only inelastic thermostat because the SN is almost.
So you are calculating numbers, right?
Yes, sir.
So I want to know how you got those numbers in your specific case. Which numbers you put in this equation so that you get finally those numbers to plot.
So actually we have to give this parameters like thermal conductivity, specific heat,
What is
and
the
energy.
T in it?
Sir,
What is the T in your case?
temperature is very good, sir. Like, that will vary, how much temperature is actually generating. That is what we are actually calculating.
So that is your extraction parameter, right?
Right.
And the specific heat,
Specific heat you are giving.
That we have to
That's
that
it.
is you are measuring or what?
No, sir. From the literature we take.
Now what about PA?
PA is the temperature generated in the atomic subsystem.
So that you also calculate? Or?
Extract. We
That is
extract.
extract, okay.
And the parameters we give is AFRT, how much energy has been deposited to the electronic subsystem, and this one is for atomic subsystem.
That parameter where you got?
Sir, from like stream calculations.
Stream calculation you got those SC and SN. Now the coupling term, how much you
So,
got? They cancel out.
from the literature, sir.
Literature is. And R is the distance.
Yeah, sir. Means
The depth,
radial distance.
The radial distance.
Yes. Around the
You think that the plot display is a function of time and
in space.
Now when the depth is going into the picture,
Sir.
depth,
Yeah, actually that term has to be added. Del X term will be added actually in case of 3 films. That I have not shown to avoid complication. Actually, that will be added in case of 3 films. In bulk, will not change.
so that term is just del X.
Means del X of
the depth is already.
it is actually we have to take cylindrical geometry for coordination. So yes. So here is the summary. So we have studied ion mixing in case of using 3 different energy regimes. In ion regime, we have seen less than 15% of total thickness. It was attributed to the limited mixing was due to nickel insensitivity. And in case of medium energy, we have seen almost 60% of mixing enhancement in the water total thickness. That was attributed to the synergistic effects of both SC and SN. And in case of low energy, we have seen almost 25% of enhancement in the layers, and it was out of 25% of total thickness. And we have attributed these effects to ballistic and thermostatic effects. So here is a scaling law. Here you can see we have plotted mixing percentage as a function of energy of ion. So in the case of medium energy, one can get more mixing rates. And here are the publications.
Before that, I have so many questions. Now, what about, because you said you saw the results, so what about the superconductivity characterization and the ferromagnetic characterization?
Our main motto was to make the.
But you said you have done that.
We have done. I have not shown it here. Means I wanted to emphasize how much mixing we have.
So here HEG only on the structural analysis, no physical properties.
In the first case, in order to confirm whether it is superconductor or not, we have measured superconducting
So where is that pattern?
That I have not shown you.
So that was necessary, right? This is on
Yes.
You should show them those kind of things. You have in backup slides, but you have
Maybe
confirmed that it is superconductor.
You can show it.
Go to the next slide
Maybe.
and tell which paper.
Which paper can contain that?
So this paper actually this is the first paper where we have confirmed the
Superconductor. First one.
And ferromagnetic nature?
ferromagnetic nature also it is there in the
First paper.
yeah. After that we haven't
Only
mentioned.
has done in case of 100 kV this time.
This is 4 bands.
The other samples you have not had. No, you understand that. That's fine.
So these are the publications related to my thesis, and these are the publications out of my thesis. And I would like to acknowledge. Thank you for your time.
Just one small question. You got this fluence. 10 to the 12 ion per.
So
The accelerator must have told you. So how did you do it?
like the question is
How did
That's
you
a
know
fluence
it?
calculation.
10
the
to
place is
the
calculated.
12.
Okay. So dose phi equal to n q d by I'll explain what this is current in the indicator. So what is the current? So ion current actually. So n is q is the charge, t is the time, and n is the counts in the indicator.
Okay, so answer. Why did you get all these numbers put together? You want to calculate phi, how did you get n, how q,
So-
who is q, what is
So
q?
it is just charge of current one.
Huh?
It is just charge of current one, and
Charge of electrons.
so Q is 1.6 and n is number count in the indicator. Like how many? So what do I say? Actually, these are n is count of ions, not ions.
P
So T is time for the
Is not their area? Information?
right.
because 4 centimeters square you have said.
Normally we take 1 centimeter by 1 centimeter. So 1 centimeter.
What 1 centimeter or 1 centimeter?
Sample size and ionium area is 1 centimeter square per 1
Did you
centimeter.
measure with your sample?
No, for ion.
No, this measurement fluence is done with your sample. You put your sample and then
No.
sample का कहाँ से आ
How do we know that this is the fluence? It will do correct. Either by time or by count. How
When we fix the time, when we fix the fluence, we do calculate the time, right? How much time is needed for this particular fluence. So there we do measure something, right? When we put the beam in Faraday cup, we measure something.
अरे देख तो बोला ही नहीं अरे वो देखा है मोटी कैसे
Yes. Yeah. Like national we can actually count the current. And current.
नहीं कहाँ so you have to tell me this yes that is what
Like this much microampere current is in the Faraday cup, and this much time will be